So, what is up, my little physics nerds? We have going over the sixth example of the energy unit. It's our first time using some energy bar charts to kind of keep track of some conservation laws. So, let's take a look at it. We have a baseball is traveling some initial velocity. So, right there, that's important to me because that tells me it's moving. Okay, and it moves the glove backwards. When the ball is caught. So ball is caught tells me that the final velocity is 0, right? And we got this glove that's moving, and it's got some initial velocity that's not equal to 0. All right, so all of these are little important things. And then part A says, construct an energy bar graph of the situation with only the ball and the earth in the system. Okay. So the ball is in the system, and that means, remember, that ball was moving. So I know it has some amount of kinetic energy to begin with. So I'm just going to put, let's see, 1, 2, 3, 4 blocks of energy. Okay. And the earth, normally we include the earth in our system if we're worried about gravitational potential energy. But in this case, if a ball is flying horizontally, it's not changing height. So we actually don't really get anything from including the gravitational potential energy because there's no changes in it. So this is pretty much it, okay, on the initial side. Now in the end, ball catches, the glove catches the ball. Ball stops, so there's no kinetic energy. It didn't change any height. You remember, we're not including gravitational potential energy. There's no stretching or anything. There's no thermal or anything. The glove took all of the energy out of our system. Now, if you remember, only the ball and earth are drawn in our system. The glove is out here. So what we need to show is that energy is leaving the system through the glove. Okay? And how much? Well, we had 4 blocks of kinetic energy, so I'm going to draw 4 little tick marks. 1, 2, 3, 4 to show the glove took all of the energy out of our system. So qualitative equation for this, remember the sum of all the initial energies needs to equal the sum of all the final energies. And so all of the initial energy that we had was kinetic energy. So all the kinetic energy ends up equaling, and we had energy right here. We had energy leaving the system. So energy was being transferred out of the system. We call that work. All right? So we say that all of the kinetic energy then turned into work. So there's our qualitative equation. And part C actually gives us some equations now, or some numbers now, and so that's going to ask us to solve for something. So say the ball was initially moving at 30 meters per second. All right, so I know that there's an initial velocity of 30. And the glove moves a distance of 20 centimeters, so I know that there's some distance moved of 0.2 meters, 20 centimeters, when catching the ball. What magnitude of force did the player have to exert on the ball to catch it? So we're trying to find some force. Okay. And the one thing that I forgot to include in the problem, and I write it right here, we're going to say the mass of the ball is a half a kilogram. All right. Boom. All right. So let's take this energy equation, we're just going to move it down here. K equals work. All right, so we're now going to plug in our equations for each one of these. So I know the equation for kinetic energy is 1/2 mass times the velocity squared. And because this is on the initial energy side of the equation, this right here is the initial velocity. Okay, and then work, our equation for work is force times distance times the cosine of the angle between those two quantities. Okay, so we need to figure out what theta is. All right, what is theta? Well, you have a ball, okay, baseball, and there's That's a glove. Glove catching it, right? Baseball was originally moving to the right. And this glove is going to move this way, 0.2 meters. And the glove, in order to stop the ball, the glove is applying a force to the ball, right? The glove is applying a force to the ball to the left. That is a force on the glove. Whoop, backwards. Force on the ball by the glove. So those two quantities are totally opposite of each other, 180 degrees. So that tells us that theta is equal to 180 degrees right there. So when I plug in a few more things, 1/2 mv naught squared equals cosine of 180 degrees is -1, so this is negative force times distance. And the problem was originally saying, hey, solve for the force acting on the ball to catch it. So my goal now is solve for that force right there. So I got to get the force all alone. I'm going to divide both sides by -d. And we're going to end up with force equals negative mass times velocity squared divided by 2d. And now it just becomes plugging in all of our values that we had. So plug in all of your values and we should end up with negative 11,250 newtons. Boom. Now remember that negative right there, remember for a vector quantity, that negative just gives us direction. So in this problem we had said to the right was positive. So because this value is negative, all that's saying is that is a force of 11,250 newtons that is being applied to the ball in a leftward direction. All right? I will see you guys around in class. Leave a comment or anything like that if you guys have questions, and I will see you guys later.